I like the way you phrased the question, love affair, because that's exactly what it was, as I see it now more and more clearly. Actually, it's interesting that when I was a student, and I was growing up in Russia, in the Soviet Union, and I was very good at math, but I didn't like it. I hated it. I thought it was such a boring, lifeless, and irrelevant subject. But that's because everything I knew about mathematics was the stuff that we studied at school. And I didn't realize that there was more, much more. So what really helped me was my fascination with the universe, with physics, with elementary particles and forces between them. I was lucky to have someone when I was 15 years old, to have someone in my life who explained to me that to understand the structure of the universe, one has to first learn mathematics. But not the kind of mathematics which I was exposed to. Much deeper, much more fascinating, much more beautiful mathematics. And so I remember that moment when he pulled a book from a shelf and he opened it and he showed it to me. And it was full of this mysterious diagrams and equations. And it was, I realized that it was a portal into this mysterious world of divine beauty. And I was just like, wow. And my mentor said to me, you think what you study at school is mathematics? No, this is mathematics. So I fell in love. And the rest is history, as they say. What I have learned as a mathematician is that the easy answers are usually not the right ones. So if we talk about mathematics, and again, if we talk about real mathematics, the kind of stuff that people like me do on a daily basis, and unfortunately we keep most of it locked away from others. So I'm trying to open the doors, and I'm trying to help others to see, to enter these museums of knowledge and beauty, which is what mathematics is about. When someone gets exposed to this stuff, and not the boring and lifeless things which people are terrified of when they are forced to study at school, then you realize that a lot of it actually, number one, have no obvious connection to physical reality, to kind of consensual physical reality that, things around us. A lot of it does, of course. I have 10 fingers, so I can count. So yes, the numbers I realized manifested in physical reality. But there are things in mathematics which are much more sophisticated, much farther removed, I would say, from physical reality. There are numerical systems which are not realized anywhere. There are infinite dimensional spaces which are not realized anywhere. We don't see them. So where are they? Well, there are some who say that we humans invent this stuff, like elaborate pieces of fiction in a kind of a game, like a game of chess. But I don't believe that to be the case. There are several reasons for that. And well, first of all, if that were so, we would be completely free to invent the rules of the game. We would be completely free to change the rules of the game. We would be, and different people would play different games. But there is only one mathematics, as far as we can tell. We all study at school Pythagoras' theorem. Pythagoras came up with this theorem 2,500 years ago. And in fact, there is evidence that in other cultures, in China and Babylon, mathematicians had discovered the same theorem even earlier. But let's just say Pythagoras, 2,500 years ago. I don't know much about Pythagoras. I don't know what he ate, where he lived, how he felt. But I know that what Pythagoras' theorem meant to him is exactly the same that it means to me. And later on, others could discover the same thing, but it would be exactly the same thing. So this kind of knowledge, it shows us that this kind of knowledge is timeless, is eternal, is unchanging. So that's very special because, for example, our physical theories change all the time. We had Newtonian mechanics, which we thought was so powerful and so beautiful, and it described almost everything we knew at the time. And it was very tempting to say that this is a final theory of physics. But of course, now we know that that's not the case. Einstein's relativity theory sort of turned Newtonian mechanics on its head. And there is no reason to believe that Einstein's special relativity, say, is a final word. The theories will be updated. But Pythagoras' theorem will not get updated. It means the same thing to everyone in the world today, and will mean the same thing 1,000 years ago. So that's one argument that you can make. There are more elaborate arguments. The great logician Kurt Gödel, who, one of the giants of mathematics of the 20th century, I would maybe say one of, really one or two most important people in mathematics of the 20th century. He actually gave a mathematical argument why it would be impossible for us to say, for mathematics to be invented. There are certain very important properties of mathematical knowledge that he had discovered, and which we now understand even better today, which show that that is impossible. That is an impossibility. It's almost like you are trying to build something. If you build something, let's suppose you want to build a ship, okay? So of course you make a ship and you don't know exactly how it will move, which way it will go, how exactly it will float, and so on. So that's okay. That's normal. You can still say, you built it, you created it. But imagine you're building a ship, and then suddenly it turns out to be an airplane. So how can you claim that you created it? So that's what, more or less, that's, as a rough analogy, where we are with mathematics. It's so much different from the kind of things that we can create or invent. So that points to an alternative, which is that mathematics lives in a world of its own, in a kind of Platonic reality. And of course, Plato was one of the first philosophers to theorize that there are certain things which exist outside of space and time, and outside of what we usually call physical reality. And so mathematics, if so, then we actually discover mathematics. So Pythagoras discovered Pythagoras' theorem, did not invent it. So we discover them by these results, these ideas, these theorems, equations, by tapping into this magical world of mathematics. That's why I think it's so important for all of us to realize that it exists. And it's kind of the irony, the paradox is that most people think mathematics is the most boring subject. But in fact, I think it's a portal. It's a portal into hidden reality. Because if mathematics exists outside of space and time, and outside of logic, what else is out there? Of course, it's not only possible, it's necessary, and it's a shame, it's a tragedy, it's a scandal that it's not happening. And one of the things, to illustrate that is to realize that our school curriculum, the kind of material that we teach, is more than 1,000 years old. More than 1,000 years old. Can you imagine that in our physics class, in our biology class, we would teach our kids the stuff which was 1,000 years old or more, and not teach them more recent stuff? We would never know about atoms and DNA and the planets and the solar system. Why is it that we do this to our kids in our mathematics classes? So people say, oh, but mathematics is so complicated. You have to first teach this old stuff so that you could get to the more recent stuff. And as a professional mathematician, I can say clearly that's not true. That is exactly the kind of linear approach to education, to our culture, which creates the kind of situation, terrible situation we are in today. I'll just give you an example. In geometry, in our geometry classes, we only study Euclidean geometry. And I'm a big fan of Euclid. he's my man, The guy wrote this book, Elements, in which not only he gave a first clear presentation of ideas in geometry, but he gave us sort of a blueprint of how to do mathematics, the axiomatic approach. You have axioms, you have rules of inference, you produce theorems and corollaries and lemmas and so on in this way. So very important, he laid the foundations for our logical reasoning in the way we discover new mathematics. But does it mean that we have to stop at Euclid? There is also non-Euclidean geometry. To make an analogy, it's almost like in literature, we had Homer. I don't mean Homer Simpson. I mean, the great author. And of course, his books, Odyssey and Iliad, they laid the foundations of the Western canon of literature. And it's super important, right? Super important. And we study them, and we must study them. But do we stop in our literature classes at Homer? No. We read Melville, and T.S. Eliot, and Salinger, and many others. And likewise, we should do the same with mathematics. We should talk about non-Euclidean geometry. What is non-Euclidean geometry? It sounds so scary. Of course, you have to first study Euclidean geometry before you can get to the non-Euclidean geometry. That's what the common wisdom says. But that's totally not true, because non-Euclidean geometry is all around us. Think about the surface of the Earth, the sphere, with its meridians and parallels. It is an arena, a realm for non-Euclidean geometry, the same way as a plane, as a flat plane, is the arena of Euclidean geometry. It's just that lines in Euclidean geometry get replaced by meridians on the globe, on the surface of the Earth. So, to put it bluntly, in our geometry classes today, the Earth is still flat. But we know that it's not flat. Why can't we tell our kids that, look, kids, the surface of the Earth is round. It's a sphere, is where you can observe the phenomena of non-Euclidean geometry, where parallel lines intersect, unlike lines on the plane. It's more fun. They will love it even more. And it will also help them understand the special role of Euclidean geometry, that it's a kind of a special abstract version of geometry, which actually we don't observe in our universe. Because Einstein also explained to us that our space-time is curved. Not only the surface of the Earth is curved, even the three-dimensional space or four-dimensional space and time are curved. A ray of light travels on a curve, not on a straight line. It is bent around the Earth. So this is more real. It's more realistic. It's something which is connected to nature, to physical reality, more so than Euclidean geometry. And we can teach that in parallel, no pun intended, with the Euclidean geometry. So this is just one example. And there are many other concepts and ideas. Some of them I talk about in my book, Love and Math, like ideas of symmetry or ideas of clock arithmetic, things which are everywhere around us. And we should open those doors and have to let everyone in on the big secret of what mathematics is about. There is a connection, and in fact, if you look at works, for example, Leonardo da Vinci, he certainly exploited the idea of symmetry, the golden ratio, the beautiful drawing he had, Vitruvian Man, in which he, we have all seen, it's kind of like embedded in our psyche, exploits ideas of symmetry. But even before Leonardo da Vinci, for sure, for centuries, for millennia, artists have been aware of ideas of symmetry. So symmetry is important, and we strive for beauty, we strive for symmetry, and we don't fully understand why. That's a very interesting question. In mathematics, symmetry takes a very special connotation. It's a very special connotation. So the idea of symmetry is actually, it's a very simple idea. The idea is that symmetry is a property. We say that something is symmetrical, or we can say something is more symmetrical than something else. And what we mean by that in mathematics, in mathematical terms, is that an object of interest allows certain transformations which preserve its position, shape and position. So for example, a round object like this, if I rotate it, if you look away and I rotate it and you look back, you won't know the difference. If I rotate by any angle around the main axis. But if it were square, and I rotated it by an angle other than 90 degrees, or 180 or 270, you would know the difference. So that's why, this one, if I rotate by an angle other than 90 degrees or 180 or 270, you would know the difference. Here, no. So every such rotation, every rotation by every angle, in mathematics we call it a symmetry of this object. Whereas here there are only 4 possible rotations which will preserve its shape. Well, let's not worry about the napkins themselves. Let's just put it like this. Okay? So,
and these are infinite. Correct?
So here there are infinitely many, right? Symmetries, infinitely many angles. Any angle will do from 0 to 360. And here only 4. 0, 180, 0, 90, 180, 270. So from that point of view, we can say this is more symmetrical. It has more symmetries. So that's the beginning of a beautiful theory. But in mathematics, we then say, okay, we're not so much interested in symmetries of a given object, but we are interested in the symmetries as forming an object of its own. That's exactly the kind of abstract object that we talked about earlier, which kind of exists in a Platonic, in my view, exists in a kind of Platonic reality to which we connect somehow through our consciousness. And so, but we can learn about the existence of this abstract object from our experience. For some experience with a round object, we learn that there is that we can look at all possible angles, and a collection of those angles, as what we call in mathematics as a kind of this abstract object called a group of symmetries. In this particular case, you can think of it as a circle, because every rotation is like an angle, so it's like a point on a circle. So there is a round object which we can see. It could be a bottle or a glass, or it could be a colon or something like that. Anything that's round, that you can rotate by any angle and it will stay the same. Right? So, but behind it lurks this abstract object, the circle. And this one circle is servicing, so to speak, all of those round objects. And in mathematics, we study that circle, its properties, and how it can be realized. And this is just the first example. There are many other symmetry groups. For instance, if you look at the sphere and look at possible rotations, then it's not just an angle, it's also the choice of the axis of rotation. You can rotate like this, or you can rotate like that. So you get all kinds of interesting things, but you can then go further and can consider infinite dimensional spaces and infinite dimensional symmetry groups, and so on. So that's where that theory has been going in mathematics. Now, the question is, what can we learn from this? How is that useful? And so of course, we are more familiar with realizations of symmetry in geometry. So for example, I talked about rotations. So it's a kind of symmetries are realized by rotations, but that's not the only possibility. Symmetries can also be realized in more abstract ways. For example, in algebra, you can have an equation in which if you replace one variable by another and vice versa, the equation will stay the same. So it's also a symmetry, but it's a symmetry of something which we cannot touch. It's an equation. So an abstract symmetry could be a symmetry also of another abstract object. Or in physics, an elementary particle could have its own symmetries. But these are not symmetries in a physical geometrical sense. They could be symmetries of a kind of inner world of a particle, if you will. So for example, an electron has spin up or spin down, and exchanging spin up to spin down is a kind of a symmetry. But it's not a symmetry which we are directly observing. It's not like an electron is flipping. Electron has its own inner world in which that symmetry is realized. And of course, what we've learned in the last 100 years of development of quantum theory is that understanding symmetries of those particles and interactions between them are the keys to understanding the fundamental structure of matter, fundamental structure of the universe. So that's one of many applications of the mathematical theory of symmetries. It is a facet of reality, but it's a very interesting question. So for me, it is a facet of reality, facet of physical reality. It can be found, it's manifested in physical reality for sure. It is a facet of our consciousness, right? And it's also a facet of this abstract world, Platonic world of mathematics. And it's interesting how these are all interconnected. And it's, so I think it's another hint maybe, another clue of what's really going on. Absolutely true. So what would make the study of mathematics so much more exciting is when students will realize how it connects to the real world, to the world around us. And the example you gave is perfect. If we observe this kind of symmetry in molecules, or even if you look at the DNA, at the double helix, it's also symmetrical in its own way. And so when we realize, or the example I like to give to kids, especially middle school, is a Rubik's Cube. So Rubik's Cube is when you rotate, the sides, these are also symmetries. And so you can realize then the algorithm that you use to solve the cube, to solve the puzzle, is actually an exercise in group theory. It's a symmetry group related to Rubik's Cube, which has many, many different elements, and they interact with each other in a certain way. So if you explain symmetries, not in a way it's usually explained in mathematics, where you say a symmetry group is something that has axioms, number one, number two, it's property like this, and axiom number one, number two. But you explain how it's realized in a specific context. Then you have a motivation as a student to study this and to learn more about this. So I was lucky to have teachers like that who were able to show me to show me these beautiful examples of where mathematics is realized. And then that gave me the impetus and the motivation to understand the abstract theory behind it, because then you realize that abstract theory could be the vehicle, the engine, which will lead you to new discoveries in the world around you. It equips you with new glasses, with kind of magic glasses through which you start seeing things which you couldn't see before. This is a French mathematician. His name is Évariste Galois. And it's a beautiful story for many reasons. He lived in the early 19th century. And he actually was killed in a duel when he was barely 20 years old. But before that, he wrote some papers, and he solved some very important problems. Not only solved them, but developed a new framework of how to approach a whole class of problems in mathematics, which actually nobody could understand at the time. It took another 40 years for these papers to be rediscovered and appreciated by others. So he was way ahead of his time. And now, of course, he's a hero, and his name is on many important objects and concepts in mathematics. But his basic idea was that the same concept of symmetry can be applied not only in geometry, as we discussed before, or in physics and so on, but also in the study of numbers and equations. So, and it's actually a very simple idea, if you, in retrospect. But he was the one to say it, to believe in it. And so for example, what kind of numbers do we know? We know whole numbers. We know 1, 2, 3, 4, 5. Of course, I can count on my hand up to 5, then up to 10, and so on. So this is very familiar. Then you got negative, you got 0, you got negative numbers. That's not enough, because you also have fractions. For example, you have if you have a pi, you cut a piece, you get a fraction of a pi. So you get fractions. We call them rational numbers, because they are ratios of two whole numbers, like 1/4 or 2/5. But that's not enough either. So there are other numbers which are kind of beyond these most obvious ones. And the simplest example is the square root of 2. The square root of 2. And so square root of 2 cannot be written as a fraction. You cannot write it as a 2/3 or whatever, as a ratio of two whole numbers. And this is a very it's very unsettling. Because, and actually, Pythagoras, for one, did not believe that square root of 2 should be allowed in the family of numbers. Because only rational numbers should be allowed. But now we understand better. We understand that all of these numbers should also be accepted. It kind of be much more inclusive. So we should accept this number. But how does this number arise? It arises as a solution of the equation, x squared equals 2. So it's natural to accept this equation and say this is legitimate. And yet its solution, square root of 2, is not the number of the same kind. So then what to do? Then we should say, okay, let's accept it as well. So we get a bigger numerical system in which we accept the square root of 2. But realize also that it's a quadratic equation, so it must have two solutions. And in fact, it has two solutions, not only square root of 2, but also minus square root of 2, negative square root of 2. So there are two solutions. So as soon as we accept square root of 2 in our family, we have to accept negative square root of 2. But then there is a trick that you can exchange them. Square root of 2 and negative square root of 2. They're like two twin brothers. You can exchange them, and this new numerical system will stay the same. So it's a classic definition of a symmetry. It's the same as our body, flipping left to right, or a butterfly flipping the wings of the butterfly from left to right. And that's what Galois realized. Realized that if you study equations like this, it's very important to talk about the symmetries of solutions. Like in this case, square root of 2 and minus square root of 2. Because until Galois, people tried to find a formula for the solution. And I think it's such a great story about how people get caught up in their preconceptions. So the idea was, if you have an equation, you have to solve it. And then they try to write formulas, solutions. So for quadratic equations, the formula for the solution, actually, we studied at school. I'm not going to repeat it, not to trigger any unpleasant memories. But, for cubic equations, so that formula, by the way, was already known to Al-Khwarizmi, the great mathematician, after whom actually algorithm is called after him. He had a book called Algebra, and from which the word algebra originated. So this was already, I think, around the year 800, so 1200 years ago. So the formula was known. maybe even before. The cubic equation was solved, similar formula. The equation of degree 4 was solved, but they could not solve the equation of degree 5, and they kept trying, hundreds of years. It doesn't work, let's try again. Doesn't work, let's try again. But Galois said, no, this is the wrong question to ask. You should not try to solve the equation. You should talk about the symmetries of the solutions. And you can talk about the symmetries even if you don't know what the solutions are. You can discern information about symmetries just from the structure of the equation. And if you do that, then you can learn, as he did, that it's impossible to find the general formula for the solution of equation of degree 5 or 6 and so on. And so he solved, not only did he solve an outstanding, a long-standing problem, but he kind of hacked it. He turned it upside down. He looked at it from a different angle. And that is so beautiful because I think the greatest discoveries in mathematics are like that. When you don't solve it in the way it was understood before, but when you see it in a totally different light. And this happens in mathematics all the time. And that's where I think we find the true beauty. Also, what's also exciting is his life story. He was killed in a duel. And we know that the night before, he was trying to finish his manuscripts, his papers. And so I can envision, I can almost like see Galois, the young 20-year-old man, sitting at this desk in candlelight and frantically writing the stuff to finish, because he must have known, he must have felt that maybe tomorrow is the end. His life is coming to an end, and he wanted to share. He wanted to share with us. So I want to think of this as like he was writing a love letter to us. And so we should take it as such. We should take it as this gift of love and use it and appreciate it. Definitely, all the time. But not only me. I mean, there's so many, there's so many stories which are known about people who, for example, see ideas and solutions in their dreams. There was a great Indian mathematician, Ramanujan, who actually never received formal training in mathematics. That was at the turn of the 20th century. And yet he was able to discover some absolutely amazing and astonishing results. And we mathematicians are still, 100 years later, poring over his notebooks and finding another gem, another jewel of insight. How did he come up with all these ideas? And well, the story is that some of that came to him in his dreams. So, what does it mean? So I think it's a great example of some unknown connections that we have to the world, to the universe. And in this day and age, we are so prone and so happy to rationalize everything and try to explain everything. But, I think we are kind of forgetting how to experience things and how to just accept things. We know that there are things we experience which cannot be explained, like when we fall in love. If you start explaining it, it means you're not in love anymore. So you either are in love or you're trying to explain it. And so, in that sense, it's clear that all of our experience points out that there are such beautiful moments, such beautiful things, for which we don't need an explanation. We need to experience them, and we should feel grateful, and we shouldn't run away from them the same way as we should not run away from love. And these are the best moments for me as a mathematician, when I feel that connection. And I don't want to explain it. I want to feel it. I want to accept it. I'm grateful for it. It's a gift. But my book is called Love and Math. And people ask me, why is it called Love and Math? And I would always try to give a clever answer. But recently I realized that I actually didn't know why. And now I think I know. And I used to give an answer like this. I would say, well, everybody thinks that they hate math, but everybody loves love. So I'm trying to put some love into math. Very clever. So people will be like, okay, that's cool. Another one was, math is kind of like love. It's simple at first, But then it can get awfully complicated. That's also a clever answer, but it doesn't really get to the heart of it. And then I realized that actually this book was my love letter also. You know, it was my love letter. To whom is another question, but it definitely was a love letter. And I also realized that why I call it love and math, because these are really the two, to me, these are two pillars of humanity. And neither can replace the other. That's why it's called love and math. It doesn't say love is math or math is love. No, love and math, the two pillars. And love comes first. That was the message. So 5 years ago, I made a film, which is called Rites of Love and Math. R-I-T-E-S, Rites of Love and Math. And this was my first experience in the arts. My first experience as an artist. I mean, in some sense, one could say being a mathematician is like being an artist also. But in mathematics is a very special kind of art, where you have very, very strict rules. And in cinema or in visual arts or music, it's different in the sense that we are much more free, kind of. Mathematics is also free, but within certain rules. And in the arts, we are kind of really, really free. And it's exciting, but also scary. Because what if you go sort of in the wrong direction and lose yourself? So this was my way to kind of lose myself and to try to speak about my deep emotions and feelings the way I see it now in the language of art. And so when I look at that film now, so many years later, I see so many things which I was experiencing, perhaps at subconscious level, which I couldn't say and express in words. And fittingly, I chose cinema as the language, the artistic language, to express those ideas. And so, and the film is about love. It's about whether it's possible to find a formula of love, a mathematical formula of love. It's a question. And it's a story in a kind of, the way I look at it now, it's sort of like a warning in some sense. It's sort of like, it's about a mathematician who thinks he found a mathematical formula of love. But then it kind of doesn't end well for him. And so I think it's it's a cautionary tale. It's a cautionary tale. And maybe it was a message to myself. Don't try to describe love by a mathematical formula. Experience it. Love math. Enjoy math, appreciate math for what it is and for what it can help you. But also enjoy, appreciate, and accept love. That's what I think the film was about. Very good question. So actually, I'm glad you give me opportunity to talk about this, about freedom in mathematics. Because there is a great quote from a great German mathematician, Georg Cantor. He's the guy who really found a framework for mathematical understanding of infinity. So it's absolutely incredible leap of in our understanding of mathematics, of the world, and everything. And his work was criticized. He personally was very harshly criticized, and he suffered immeasurably from this. But he was true to himself, and he knew that it was his mission to give us this gift, and he did. But at one point, the criticism was that you can't do this. You're not allowed to do this, the kind of stuff that he was doing in his works. And his response was basically, yes, I can. Yes, there are rules, but I'm doing everything within those rules. And within those rules, I am free to go as far as I can. And he wrote that because the essence of mathematics lies in its freedom. So it's very important. So in this sense, it's very close to art. Mathematics is close to art, is in that you have to free your mind, you have to free your imagination, and you should not be afraid to go as far as you can, as far as your ideas, your intuition, as far as your thoughts take you, and should not be afraid. And so it is as true in mathematics as in other areas of human endeavor. In mathematics it's special because it seems that this territory is much more delineated. The rules, there's a framework, there is a more rigorous framework. But this example, this story shows that even within a rigorous context, a rigorous system, you can either be afraid and stay inside the box, so to speak, or you can break out of the box and do something completely different and blow everybody's mind, which is what Cantor did. And so that is the aspect of freedom and being free and being not afraid, which is so important everywhere in life, but also in mathematics. And I think the greatest discoveries were made precisely because people who made them, they had no fear. They were very courageous to do something, to make the next step, which no one was able to do before.